All right, good day, Year 11s. Welcome to the next lesson of our Year 12 content for matrices. I'm hoping that you've completed the previous chapter, which was on these questions, 11F. Now, I know I said we wouldn't do these, but it's just good for revision, as it will be quite useful in the next topic. But moving on to 12A, we're going to continue with our main matrices stuff. So for chapter 12A, what we're looking at is inverse matrices. Okay, inverse. Now, if you remember back in year 10, you would have seen this word called inverse. Now, the inverse, you could say, is the opposite of something. And what that something that we're referring to is, let's say, for example, you've got addition, okay, as your value or a positive value. What is the inverse of a positive value? Well, it would be minus. So let's say this is our operator. The inverse, okay, is the opposite. So the opposite of plus or positive is minus. The opposite of minus, okay, would be positive. And then for multiply, the inverse would be divided by. And for divided by, the inverse would be multiply. Now, when it comes to matrices, some of these inverses are a little bit different. So we don't technically use these inverses when we're trying to solve and work with matrices. When it comes to matrices, the inverse is a little bit different in that instead of multiplying or dividing to find certain things, we use what we call an inverse, which is, for the matrix, it's a power of -1. Okay, so if you have, for example, this matrix, 2, 3, 4, 5, all right, just as an example, the inverse of it would be to the power of -1, not minus or not divide or multiply, because we don't really know what the values are in here, although they are all positive. But when we inverse a matrix, it's going to be to the power of -1. Now, this will come useful later on when we're solving equations and deciphering messages and that sort of thing. But for now, let's learn how to get an inverse of a matrix. Okay, so some rules that you need to understand when it comes to matrices and inverses. Only square matrices have an inverse. When we talk about square matrices, that could be a 2 by 2 matrix, could be a 3 by 3, 4 by 4, 4 by 4, 5 by 5, whatever it is. Okay, it's basically a matrix that's square, so that means it's the same number of rows, same number of columns. Okay, only those sort of matrices can have an inverse. Okay, so for example, let's say that you've got matrix A, whatever it might be. It's a square matrix, so let's say, I don't know, a square matrix of, let's go with a 2 by 2. Let's say it's like 1, 3, 2, 0. Okay, if this is a matrix, then its inverse, okay, if we try to work it out, it's got an inverse. Okay, well, the inverse of it would be a to the power of -1, and whatever that is. So if I equated this and I went to the power of -1, now that matrix, whatever that matrix would have been, if I multiplied this with its inverse version, I should get, okay, so if I multiplied it with A, which is that matrix 3, 2, 0, to the power of -1, I should get what we call an identity matrix. Okay, so the identity matrix is going to have the same order as A. So this A matrix and this A inverse matrix, they're going to have the same order. So that's our 2 by 2. And every number on the leading diagonal is a 1. So that means every number diagonally is going to be 1. And all other entries will be 0. Okay, so let me test that on my calculator for now. Okay, if I have, for example, okay, A matrix, let's go 1, 3. Now I just made these up, I hope they work. 2, 0. And I multiplied it with its inverse version. So 1, 3, 2, oops. to 0. Remember, the inverse version would be to the power of -1. I should get, there you go, the identity matrix, which is that. So these two matrices are somehow related to each other. Okay, where this matrix here is matrix A, and this is its inverse version, or its inverse brother, you could say, if you want to call it that. Okay, let's move on. So there's a couple things that you've already learned just now. So you've learned that matrices have a inverse. So if this, for example, is matrix A, it's got an inverse version where you put it to the power of -1. And if you multiply them together, you should get an identity matrix. So that if matrix A was, say, for example, a 3 by 3 and it had 3 rows, 3 columns, multiplied by its inverse version, you'd get a 3 by 3 inverse or identity matrix. Okay, so this only works with square matrices. Okay, so hopefully I haven't lost you yet, but let's keep going. So if you have matrix A and matrix B and they're inverse matrices of each other, then that means A inverse should equal B inverse. Now what this is saying is basically A and B. So if you have these two matrices, you'll get a question like this where you get matrix A and matrix B. And then you've got to prove if they are inverses of one another. And if they are, what this part is saying is the inverse of A should equal whatever B matrix is, and A should equal whatever B inverse was. So on my calculator, what that's saying is, let's say you have matrix A. I've already put these two. Actually, let's use these matrices here. Okay, so if I have this matrix 1, 2, just going to repeat it, 1, 3, 2, 0. Okay, let's call that matrix, I don't know, control VAR, let's call it matrix D. Okay, there's matrix D, and the inverse of matrix D, so if I go D to the power of -1, gives me that. So these two matrices are somehow involved with one another, or the inverses of one another. So let's say I go matrix A, or D, sorry, I inverse it, right? I'm just repeating myself, but I inverse it, and I get that matrix. Now if I get this matrix, and I inverse that, I should go back to the original matrix, which is that one. Okay, so they're both related to each other. That's what this is saying. Okay, if matrix A and B are inverses of one another, then you should get something like this. So let's see if this makes sense with these two matrices. So if you have matrix A and matrix B, you're going to get a question where you got to show that these two are inverse matrices. So remember back here, if you multiply a matrix with its inverse, you should get its identity. Okay, so because these two are 2 by 2 matrices, the identity matrix in this case should look like this. So 1 on the leading diagonal and 0 everywhere else. So if you multiply these two and they're inverses of each other, they should equal that. Okay, let's test it then. Okay, so we're going to multiply them. 3, 1, -2, -1. So that's matrix A. Multiplied by matrix B. So you're going to need to know how to multiply these matrices and how to do matrix multiplication. Okay, let's multiply them together. Remember, it's row by column when you do this. Give yourself ample space to complete this. Okay, so the first one, 3 by 1 is 3. So I'm going this, and then these two. So 3 plus 1 times -2, okay, is -2. Okay, that's the first one. Let's go with the next. Let's go with the next one. So this row by this column. Okay, so 3 times 1 is also 3, plus 1 times -3 is -3. Okay, that's that. Next one, this bottom row by this first column, So 2 times, or negative 2 times 1 is negative 2 plus negative 1 times negative 2 gives you a positive 2. So just 2. And last one, so now we're working with this row, this column. So negative 2 times 1 gives you negative 2. Negative 1 times negative 3 gives you positive 3. Okay, so let's evaluate this. Okay, so remember, what we're trying to prove is these two are inverses of each other. And if they're inverses of each other, if we multiply them, they should equal that identity matrix. So let's prove that. I've multiplied them. Now let's finish by evaluating them. So 3 plus negative 2 is 1. 3 plus negative 3 gives you 0. Negative 2 plus 2 gives you 0. Negative 2 plus 3 gives you 1. And see now how I've got my identity matrix. So they must be inverses of each other. And it should work as well if you went B times A. Okay, and I'll put that in a calculator now so you can see. So we don't have to work it out by hand. But if I went, and I've labeled these already, so I've got matrix just to show you guys. If I press A, I've got that matrix there. And if I press B, I've got that matrix there. So if I went A times B, okay, that should give us the identity. Cool. And if I went B times A, it'll do the same thing. It'll also give us the identity. So that means A and B are related to each other. And if you've got matrix A, its inverse is this matrix. And if you've got matrix B, its inverse is matrix A. So they're both inverses of one another. Okay, and that's how we prove them. So again, to prove whether two matrices are inverses of each other, multiply them together. And if it gives you the identity matrix, then they are definitely inverses of each other. And remember, the identity matrix is basically a square matrix where the leading diagonal are all ones and every other value is 0. Now you can have a 3 by 3 identity matrix as well, so it might look like this, or a 4 by 4. I'm not going to draw that, but just understand identity matrix looks like that. Okay, let's move on. Okay, hopefully I haven't lost you guys, so let's keep going. Now, when it comes to finding the inverse of a matrix, there's a couple of things that we need to know. Firstly, we need to determine whether a matrix actually has an inverse or not, because not every single matrix, even though it's square, will have a inverse version of itself. Now, in order to do that, we use what we call the determinant. So you've got to find out the determinant of a matrix. So basically, the determinant of a square matrix is a number that is involved in finding an inverse. And again, it determines whether a square matrix has an inverse. Now, we're only going to do this with a 2 by 2 matrix. When it comes to 4 by 4 and any other type of matrix that's square, you can do it on a calculator. But for a 2 by 2, this is what we use. Okay, so this is the formula that we use right here. If you have matrix A, and if it's a square 2 by 2 matrix, label each entry as A, B, C, D in the following way. So the top left is A, top right is B, bottom left is C, and the bottom right is D. And then we use this formula to find the determinant. A times D minus B times C. So let's say, for example, okay, I've got a matrix 1, 2, 3, 4, okay, and I've labeled it A, B, C, D. Okay, to get the determinant, remember, the determinant is A times B. Sorry, A times D, my bad. Take away B times C. Okay, so in this case, it would be 1 times 4, take away 2 times 3. So the determinant here is 4 take away 6, which equals negative 2. Now, because there is a determinant, that means that there is an inverse. Okay, so once you figure out that there is a determinant, you can now find the inverse. So the continuation of that. So you can see down here. So this formula does look quite long. I know it looks a bit scary. Okay, but we've already done half of it. Okay, and the first half is finding the determinant, which is down here. Okay, so once you do the determinant, okay, all you got to do, okay, is get 1 and you divide it with your determinant and you multiply it with this version of matrix A. Okay, so this matrix is basically a mixed up version with some negatives of the original matrix A. Okay, so what this formula does is it gives you the inverse. You're going to need to know how to do this by hand. I'll go ahead and show that to you in the next page. But for now, to understand if a matrix has a inverse, you need to find its determinant, because the determinant will tell you if an inverse exists. And if it does, then you can go ahead and use the rest of this formula, okay, which is the inverse formula. Okay, so this is the inverse formula for a 2x2 matrix, and it's basically 1 divided by your determinant. So remember, this here is the determinant. Multiplied by the mixed up version of the original matrix that you had there, of whatever matrix A was. Now, here's the thing. The determinant is important because if you've got a determinant, that means there's an inverse. But if you don't have a determinant, okay, which or another means what that means, if your determinant is 0, then that means the matrix does not have a inverse. And what that would mean is basically, like I said, there's no inverse, and it's what they call a singular matrix. Okay, you'll see this in a calculator if you try to work this out. If you try to work out the inverse of a matrix and it doesn't exist, it's going to say singular matrix. Okay, so it's a unique matrix, doesn't have a inverse of itself because the determinant is 0. Okay, so if, let's say, for example, we'll come up with an example of a matrix that has a determinant of 0. Let's go with, let's just make this up, 1, 3, 2, and let's say that's 6. Okay, so again, let's find the determinant of this. Label the corners or the elements or the values A, B, C, and D, yeah? Okay, so remember the formula for the determinant. It's A times D minus B times C. So if I worked this out, A times D, so that's 1 times 6. Take away 3 times 2. So what would that give us? 6 take away 6. So the determinant will equal 0. Okay, and what that means is it's a singular matrix, and that means it has no inverse. Okay, because, well, if you go 1 divided by 0, it gives you nothing. Okay, and that basically means the matrix has no inverse of itself. All right, let's apply this, okay, to some of these questions. So consider the following matrices. Consider whether, for these ones, we need to calculate the determinant, and then B, state if the matrix has an inverse, giving reason for your answer. If the matrix has an inverse, write it down. Okay, so you need to be able to do this by hand, which is what I'll show you now, but you can do this on your CAS. Okay, so if we now calculate the determinant of matrix X. So matrix X, let's start with that. We'll do Y next time maybe, but let's do X for now. So if this is X matrix, 1, 4, -2, 3. Label the matrix in case you're confused. So that's A, that's B, that's C, and that's D. Okay, and let's find out the determinant. So the determinant formula, remember, is A times D, take away B times C. So in this case, it's going to be 1 times 3, take away 4 times -2. So in this case, the determinant will be 3, take away 4 times -2 gives you -8, but because of these two negatives, it becomes a positive. So the determinant in this case is 11. Okay, so that guy definitely has an inverse. Okay, let's quickly work out y and see if y has an inverse. So for y, the matrix is -3, 1, 6, -2. So that's A, B, C, D. And so the formula, remember, is A times D, take away B times C. Remember, this will tell us if an inverse even exists. So if it doesn't, that means that we can't do an inverse. So, and that if the answer is 0 from this. So that's going to be -3 times -2, take away, oops, sorry, 1 times 6. Okay, so if the answer here is 0, that means it has no inverse. So it's a singular matrix. -6 take away 1 times 6 is 6. Oh, sorry, this is +6. Okay, so the determinant in this case is 0. So that means matrix Y is a singular matrix. So let's write that down. Singular where the determinant is equal to 0. Okay, so it doesn't have A inverse. So let's just keep going with matrix X, sorry. So we know that matrix X has a determinant of 11. So now we can continue on with finding its inverse. So hence, state if the matrix has an inverse, okay, and giving a reason for your answer. So for this part of the question, all we just write is matrix X has a determinant of 11, or matrix X, sorry, and therefore has an inverse. Okay, so if it has an inverse, question C, write it down. All right, so question C. Now that we've determined that matrix X has a determinant, we can now use, remember what I showed you guys here, that inverse formula, okay, to figure out if it has an inverse, or well, to figure out what the inverse is. Okay, so remember the formula for the inverse is going to be 1 divided by, you can say the determinant, but according to the formula it was, well, yeah, A times D minus B times C, which is basically, again, that determinant formula, which is 11. So I'll just write it all here so that we're not getting confused. But if you understand, you don't need to then put this in. You can just write down whatever the determinant is. Okay, multiplied by, and I forget this sometimes because it is a mixed up version, okay, of the original matrix. So you can see the mixed up version there is D, negative B, negative C, and then A. So A and D are swapped, and then B and C are given a negative. Now, just watch out for that, because if your values are already negative, if you give this guy a negative, it'll become a positive. Okay, so that's just something to watch out for. Or another way you can think of it is you're multiplying it with a negative one, but I don't want to confuse you anymore. So let's just say that that's D, that's A, they get swapped. B and C are given a negative. Okay, so let's work this out. Inverse is equal to 1 divided by, now, A times D minus B times C. So matrix A was 1 times matrix D, which is 3. Take away B and C, so 4 times -2. Multiply by the mixed up version of whatever the original matrix was. So see how D was 3 and A was 1. They get swapped. So 3 now goes up here, and the number 1 goes on the bottom right. Now 4 was originally a positive, but because we're giving it a negative, it becomes a -4. And C is a -2, so if you give it a negative, it becomes a +2. Okay, so let's evaluate this. 1 over, and remember the determinant, this guy down here was the determinant. We found that the determinant was 11, so it's going to be 1 over 11 multiplied by 3, negative 4, 2, 1. And we just multiply all that, kind of like what we did with the scalar multiplication. So that'll be 3 over 11, negative 4 over 11, 2 over 11, and 1 over 11. Now that felt like it took a while, okay, but you need to know how to do all of this by hand, okay? So make sure that you understand when it comes to these matrices, find the determinant first, okay? And if it has a determinant, then go ahead and use that inverse formula to find the inverse of it. Okay, now this is all doable on the calculator. So if you have your CAS with you, follow along with me and we'll do it together. All right. So let's say this matrix here, let's make that. So let's press this button, go with the 3 by 3 there, and then press OK. I can see it's a 3 by 3 matrix there. So, okay. Now to label a matrix, put your cursor all the way to the right, press Control VAR and then whatever letter, but in this case, let's just call it, because I've already used A and B, I might choose D. Okay, so every time I press D, it'll give me the matrix. Now you don't have to label it, but it just makes it a bit easier, I guess, if you prefer that. But to get the inverse, remember, inverse is basically to the power of -1. Okay, and you can see it's a bit different there, but if I press Control Enter, I should get the same decimal values. So there's the inverse version of my matrix, which was D. On your calculator, it's that easy. So I could even go back and test that we did all this correctly, okay, by finding the inverse of this matrix. Okay, so if I went here, square matrix, 1, 4, -2, 3, and then I did it to the power of -1, okay, I should get those values, which I did. So 311, -411, 211, 111. And lastly, if you wanted to find the determinant of a 2 by 2 matrix, or any matrix written by the calculator, we type in DET, open bracket, and let's say we've tried to find the determinant of this matrix X that we were working with. We got 11, right, as our answer, but let's do it on a calculator. So DET, put your matrix in there, so you've got 1, 4, -2, and 3. Close bracket. So enter, and determinant is 11, as we can see. But that's how we do it on the calculator. Okay, so you should be able to do it by hand, but later on there will be questions where you can do it on your calculator. All right, we'll skip this part. What I'd like you guys to do now is chapter 12A. So do those questions for me. If you have any questions, please message me on Teams. Thank you.